Thanks a lot, Mark. And maybe I can then, since we are a little bit ahead of time, take this opportunity to make just a few announcements or comments. Also, because I see that there are so many new people in the chat today compared to the previous discussion. So I think it's good to just remind people how these discussions and so on work. So before, let me just make a small comment about Slack. So I'm very happy that many people are using Slack and writing lots of interesting questions, and also I think very useful after the conference, posting many useful references that we can all go back and check out later. So in that sense, please use Slack, and feel free to already use other sessions that are in the future. For example, for Thomas, it probably doesn't make much sense to use today's string phenomenology Swampland discussion to have questions about JT. Maybe you can put the questions on the average session discussion that we will have on Friday. So feel free to already spread out through these other sessions, not only making suggestions for things to discuss, but also asking more questions about the talks. And I hear Slack pinging. Probably people are following my advice as I speak right now. So about this discussion. So let me remind what the idea is. The idea of this discussion is to have this more formal component of the conference so that we are all seeing each other. So do turn on your cameras when possible and engage. And these discussions, they have two parts. So the second part is the more informal part. And the second part is the one that should take about 30 minutes or more. As you have been seeing, I'm not very strict with closing it. We put all these discussions right before the coffee break, besides because if you are having an exciting, engaging discussion, we can go a little bit into the coffee break. It's not a big deal. So those 30 minutes are more relaxed. Raise your hand if you want to ask questions or make comments. And if you want to ask a question or make a comment, which is very much related to what is being discussed right now, besides raising your hand, wave so that we know that your question or comment is not to open a new topic, but to finish or continue discussing the topic we are discussing now. And of course, Gary and Mirjam, if you see someone that makes more sense to call than the next person in line, just jump ahead and invite that person. Don't wait for me. And of course, you are the coordinators. So that's about 30 minutes of informal discussion. And let me just say a few words about the first 20 minutes. The first 20 minutes, what we did and what we asked Gary and Mirjam and all the people that are giving this discussion is to do as they please. So these 20 minutes are the period of time where slides are allowed. So in this 20 minutes, and people can do everything, whatever they want. In particular, if you want to invite other people to give some small comments and have some slides on while these other people give a few remarks with slides, that's fine if it's during this first during this allotted 20-minute of let's call it slide time for preparation of the informal discussion. So that's indeed, for example, what Mirjam and Gary are going to do. They're going to have a few people during this introduction period say a few words. And of course, this announcement doesn't count towards this 20 minutes. So I will now pass it over to them and turn on my stopwatch on my phone and start counting. So thank you very much. And Gary or Mirjam, I don't know who goes first, please take over.
Okay, so I think I'm going to start. And I would, of course, like to thank the organizer for inviting both Gary and myself to lead the discussion session on the progress of constructions of solutions of string theory for particle physics and cosmology, and the directions that may be pointing towards string universality. We have decided to start with the introduction over first 20 minutes by first starting with a status report of particle physics constructions, which I will present briefly. And then in part two, Gary will continue with somewhat broader issues, including also moduli stabilization and cosmology implications. And then for part three, we have decided to give opportunity to the next generation of participants in this program to present further comments and outlook in the order of Miguel Montero, Pablo Soler, and Ling Lin. So let me start with part one. where I would like to present the status of particle physics constructions from string theory. And I will first focus on what is the current state of the art in three family standard model constructions on globally defined, primarily Calabi-Yau compactified spaces. So from its original inception, the heterotic string theory was the most promising candidate for particle physics model constructions. And actually later on, it led, among other important developments, to the first standard model, actually minimal supersymmetric standard model with only one Higgs doublet constructed by Bouchard and Donaghy. And later on, the broader analysis of big landscape of three family standard models was developed using complete intersection Calabi-Yaus, and I hope that Lara will say some more on the stages of those constructions. With the advent of D-branes, the type 2 string theory came in the game for particle physics constructions, and in particular, the intersecting brane constructions had very geometric origin of appearance of chiral matter, where also conformal field theory techniques could be employed. And within this context, one also arrived at the first examples of the three family standard models and further landscape analysis. I would say that those models suffer from phenomenological issues. In particular, typically the chiral exotics there, which to some extent may be associated with the limitations of the type of compactified spaces we could employ to obtain the full gauge and charge matter spectrum there. The last 10 years have seen a revival of F theory for its application to particle physics constructions. So the theory itself reaches to the strong coupling regime, where the nature of the singularities, the geometry of the singularities of the elliptically fiber Calabi-Yau fourfolds determines the gauge structure as well as the full chiral particle spectrum of the theory. For direct particle physics applications of standard models, the Torich techniques actually provided the first example of three family standard models with no chiral exotics, and soon after actually led to a huge landscape of quadrillion standard models with gauge coupling unification as an additional bonus. The most recent program is focusing on the leftover aspect of the matter spectra, which is vector-like matter spectra, which are harder to determine in this context, and more recent effort highlighted or developed more quantitative techniques to study the domain of moduli that would determine the particular jumps in the number of vector pairs, in particular application of the so-called Brühl-Noether theory, and some also machine learning techniques. As far as quadrillion standard models go, there are further complications there because the actual vector spectra is associated with the so-called root bundles, which leads us again to another domain of algebraic geometry. And in particular, we are moving toward the direction of determining really the exact mass spectra and the domain of existence where we have only one vector pair of Higgs doublets there. And maybe if time permits, at some later point, Martin Bies can comment further on the outlook of these constructions. So I have sort of put you, in the I brought you to the state of the art of the constructions of particle physics models, in particular 3 family standard models, which were all based on globally consistent, globally defined compact spaces. So in general, these constructions by the definition include quantum gravity, and we expect that these global consistency constructions that keep quantum gravity in play will further quantify constraints on allowed gauge structure, including global one, and the allowed charge particle matter spectrum in this context. And so the ultimate hope in this program is to uncover more and more of universal structures of string theory, and possible the existence of now unknown deeper symmetries that this theory may hold. Of course, in this program, we are really only scratching the tip of the iceberg. And especially approaches are very limited from the top-down perspective, really top-down string theory constructions, and in particular in 4 dimensions, the constraints, universality constraints are extremely limited. As far as F theory goes, the geometric origin of this theory may provide promising range of constraints for structures, including allowed representation for matter spectrum, and some progress has been done by Waddy and company, but also constraints on allowed matter representations in the presence of additional U1s, as well as bounds on allowed number of U1s, and so on. There were also other approaches which I would think may not be as top-down as one would want to have them. And nevertheless, this is a big program, and we've seen some of the nice developments there from a beautiful talk by Irina this morning. Let me also maybe mention some things that there has been more top-down progress in determining constraints on the charge and gauge structures in higher dimensions, and in particular in 8-dimensional cases, where we believe we are very close to the complete classification of global global constraints of all the allowed gauge structures. And what one has uncovered in this context is the important role that higher form symmetries in this effective field theories play, interesting role, and resurrection of string junction approaches, cobordism, the techniques of heterotic string, and so on. And some of it was also highlighted in Kumran's talk this morning. I hope that also further comments and outlook will be made by Ling, Miguel, and Pablo. So I have tried to highlight some developments in the gauge and charge sector of string theory compactification by focusing on implications for particle physics. However, we all know that there is an elephant in the room right now, which has to do with important complementary issues, not only gauge and charge sectors that I focus on, but there are issues of modularized stabilization, supersymmetry breaking, cosmological implications, dark matter candidates, and so on. All those important issues may not be unrelated. Actually, we expect them to be related. And that brings me now to the part 2 of the discussion, and I should give the screen to Gary. Thank you.
Let's thank Mirjam while Gary sets up the screen share.
I have to stop. Oh, it's already good.
Yeah, it's already good. Yeah.
So you can see my slides, right?
Yeah, just to let you know, we are at the 10-minute mark right now.
Oh, okay. So I would also like to thank the organizers for the heroic efforts in putting together this big conference, especially in these trying times. So my task, like Mirjam's, is to give you a little pep talk to warm you up for hopefully a lively discussion. Now, different approaches have been taken to connect string theory with particle physics and cosmology, traditionally, we start with what we know about the UV and construct models. Then we compute to the best of our knowledge the low energy effective field theories. Predictions are then drawn from these EFTs. As Mirjam nicely summarized, this approach has had some successes. And I myself, for instance, have devoted a good deal of my research effort practicing this approach. Now, a question that we often get asked is whether the phenomenological properties of these top-down constructions are genuine lessons from string theory or merely features of specific models. Now, some of these features are certainly model-specific, but it's fair to say that there are some general lessons we have learned. For example, the absence of exact global symmetries, restrictions on the gauge and matter content of the power spectrum, a soft UV behavior of scattering amplitudes, and the ubiquity of moduli and dualities. Now, we first came across these lessons through the world sheets, but by now there are new evidence and new perspectives on why these lessons may hold more generally. So the question is whether we can elevate these observations to some general principles. Now, there are numerous examples of what we thought was impossible before the second string revolution that have now become possible. So are we sure that we're not looking under the lamppost? But if we can identify the general principle behind, these are universal lessons that go beyond our current knowledge. The goal of the Swampland program, as Irina nicely reviewed this morning, is to identify these general principles using a variety of theoretical tools, and the list of tools just keep growing. Now, the proposed Swampland criteria are not random guesses. They are often sharper versions of the general lessons we have learned. For example, the weak gravity conjecture and the cobordism conjecture are cousins of the observations that there are no global symmetries. And various distance conjectures are manifestations of the rich duality symmetries. Now, this approach is sometimes misunderstood. So I hope we can take this opportunity to talk things out. First and foremost, the Swampland program does not undermine the importance of constructing top-down models. So explicit string constructions have in the past suggest novel observational signatures that phenomenologists and cosmologists may otherwise overlook. And during the discussions, we could certainly bring up some examples. And having explicit models is also useful for drawing lessons. So serious practitioners of the Swampland would not dismiss a model based on some conjecture constraints on quantum gravity unless these constraints are proven. But with the same fairness, we should not dismiss these Swampland conjectures simply because they are not yet proven. At the very least, we should take them as important warning signs. Now, the Swampland has offered complementary insights that the traditional model building approach does not give us. And I hope we could all agree that finding phenomenological consequences of string theory is a tall order. It will likely require every insight we could get. Now, a general lesson that we can all agree on is the ubiquity of moduli in string theory. Before we fix this moduli, we don't know what is the vacuum. It's associate low energy degrees of freedom and the physical couplings. So stabilizing moduli is a prerequisite for any phenomenological or cosmological discussions. An important observation that highlights the challenges was made by Dine and Seiber in the 80s. The Dine-Seiber problem can be summarized as the tension between stabilizing moduli and calculability. So it's easy to see because physical couplings are vacuum expectation values of scalar fields, that a local minimum can only occur if there are two terms, at least two terms of different order that compete. Otherwise, you have a runaway behavior either to strong or weak coupling. The situation for de Sitter is slightly worse as they require a balance of at least 3 different order terms. Now, if terms of different order compete to give a minimum, why aren't the higher order terms that we ignore important? Now, the large number of flux choices made it possible to find minima at weak coupling, and therefore avoiding this Dine-Seiberg runaway. But if the number of flux vacua is finite, as in most constructions, because of the tadpole constraints, the stabilized coupling, while can be made weak by tuning, is not parametrically weak. So an exception is the constructions of DGKT, which find infinitely many ADS flux vacua, because one of the fluxes is not subject to Gauss law constraint and is unbounded. However, careful study of various contributions to the potential shows that parametrically weak coupling de Sitter vacua still cannot be realized. Now, other people in the audience may have other examples that could potentially evade this Dine-Seiberg problem. For instance, either we could discuss these examples and how controlled they are during the open discussions. Now, one can also argue that because there are so many scalar fields and not just the dilettante shown here, could the expansion in various scalars conspire to give a discrete family of parametrically weak coupling de Sitter minima? We gave an argument why this does not happen. An exponential fall off is a universal behavior in any direction at parametrically large distance in field space, and not just when we consider the string coupling. So in a sense, it is a stronger results than the Dine-Seiberg problem. Now, having no parametric control doesn't mean that there's no control. The standard model couplings are not parametrically weak. But this motivates us to carry out more careful studies of de Sitter vacua, going beyond what have been done, which are mostly at the level of 4-dimensional EFTs. And existing de Sitter constructions often involve a balance of classical perturbative and non-perturbative contributions, making the estimation of error challenging. And I believe this will be discussed in more details in tomorrow's discussion session. And Pablo will also highlight some progress made as well as remaining challenges. Now, another example to illustrate that having small parameters does not mean having control on the EFT are the positivity bounds that we heard about on Monday. So let's start with QFT without gravity because the results are well established. So to an EFT, to an effective field theorist, this Wilson coefficients of the relevant operator. Okay. So they are arbitrary constants. However, negative Wilson coefficients, no matter how small, would violate unitarity and causality. So this is an example of that small parameters can drastically change the quality of the theory. So gravity introduces subtleties to these positivity bounds. For example, graviton exchange dominates the forward limits of the 2-to-2 scattering amplitude and diverges quadratically in the high energy limit. This violates the Froissart bound. And in string theory, this UV behavior is tamed by an infinite tower of higher spin states. And as Leonardo and Simon explained on Monday, this Regge boundedness is assumed in the S-matrix bootstrap approach to derive quantitative bounds on the high derivative couplings in gravitational theories. And this gravitational positivity bounds were also used to derive the mild form of the weak gravity conjecture. I was supposed to say something about UV sensitivity of inflation, but in the interest of time, I skipped that. So just to wrap up, so when I first started working on string phenomenology, it was considered by some to be the poor cousin of the clan. But the subject has advanced, and it is now interacting actively with other members of the strings family. So I think this shows progress and signs of a very forward-looking field. And in this spirit, we have asked 3 next-generation practitioners to come up with what they think are the outstanding questions. So let's hear from them before we have an open discussion. So I think the first to go is Miguel.
Mm-hmm. Okay, Gary. So thanks a lot for sharing the very nice spotlight with us. Since this is a discussion and we don't want to be overbearing, we'll be super quick. So I have a couple of questions where I think the Swampland can say something very interesting about particle physics, And I'm not alone in here. So we had a poll in the Swampland seminars and open mic events, which is something we've been carrying out for the past few months, and we'll probably be back to it in the fall. And this is the mailing list in case you want to subscribe. And so we asked this question, and you see that most people are interested. They think that the Swampland has the best potential of saying something in questions where particle physics talks to cosmology. So maybe next slide. Okay. Gary, could you? Yeah, thanks. So I just related to this, I just have two questions, which were raised in Irene's talk this morning. So first of all, there's this coincidence between the neutrino mass scale and the vacuum energy scale. And that's, I think that might be a coincidence for the tantalizing question in which the Swampland can possibly see something. And there's been a number of ideas related to the aliens distance conjecture, no-consider conjecture, and also this festina lente proposal that we had with Thomas van Riet, Kumbrun, and Herben. And I think Gonzalo is gonna talk about this in the Dawn show. And finally, there's an important question everywhere in the Swampland research, which is what is the role of discrete parameters or discrete symmetries? Something like the Wigger conjecture doesn't tell you anything about the IR. If you're not able to say, you say there's a light particle, but you say what its charge is, then you cannot, it doesn't really constrain the IR. So we really need to find arguments to constrain this value of n. And this problem is pervasive, is related to the order of discrete symmetries in the Swampland, and also to the issues of scale separation, as you can see in that paper in the bottom. So Pablo?
Thanks. Gary, can you? Thanks. So I want us to make some brief comments and pose some questions about string theory and cosmology. Gary already suggested some of the abstract problems, but I want to focus on two particular technical aspects. I will focus on those that were most popular in the Swampland poll, which have to do with the Sitter constructions in string theory. And in particular, I will focus on the KKLT construction. And I want to bring up two technical aspects that we've made progress in the last few years. One where we've clarified some potential problems, and one where new potential problems have been brought up. The first one is an apparent puzzle that seemed to appear between the four-dimensional description in 4D supergravity of the KKLT effective action and its avatars in the 10-dimensional action of type 2b. We found out that that potential class was just a consequence of not having full control of the D7 brain action in up to quartic order in Gaugino, which played a crucial role in KKLT. So in that regard, I think that's one particular possible puzzle where actually the path has been clear for KKLT. But at the same time, new potential problems keep coming up. So I'd like to bring up in particular this potential one of the singular bulk problem that says that generically in KKLT compactifications in the regime where one can lift to the sitter, the bulk does not look like a smooth geometry, but it becomes singular in an order one chunk of the bulk. There's many more progress and recent insights that we'll be covering the rest of the discussion, but I just want to ask the audience how they feel about these technical problems towards the sitter or also towards the scale separated ADS, whether they will be cleared or whether they will go towards more swampy regimes. Lin.
Okay, thanks. Yeah, so I will just make a few short comments about the universality or the lamppost principle. So as Irene introduced in her talk, the idea of universality or the lamppost principle is that all consistent effective descriptions of UV complete gravity is realized in some corner of the string landscape. And if we want to prove that, and at least for a class of theories, then I think what we should do is really scrutinize the physical arguments that correspond to the boundaries between the landscape and the swampland by inspecting the geometric constraints that prohibits us to construct these theories that lie in the supposedly swampland. And I think the geometric boundaries, constraints that in part shape these boundaries really can teach us about perhaps yet unknown physical consistency conditions. Another interesting point that also Ian mentioned is that some features of consistency quantum gravity seem to appear also in CFTs, for example, the CFT distance conjecture. Another class of models that has similar kind of structure is rigid structure is indeed the 60 superconformal field theories. And so far, we don't know of any concrete 60 theory that does not have a string theory realization. Yet, of course, there is by no means settled that if this is actually a physical principle behind this exclusiveness. So finally, I think it's a good time now to maybe explore some synergies between the Swampland kind of approach and maybe some of the ideas that was discussed in the Monday session on bootstrap and positivity, and perhaps also holography, in order to maybe find really some deeper underlying structure of all these conjectures in Swampland. So yeah, this is just some of the ideas that we had. Yeah, we will now let the public talk and share their ideas and comments. Thank you.
Okay, let's all thank all the participants in this first introduction, and Gary and Mirjam and Ling, Pablo.
Thank you.
So yeah, let me just, before opening the floor, also remind people that tomorrow there are two discussions that are not unrelated to this one. And in particular, there is one by Eve and Daniel on cosmology, and then in particular on string cosmology, and the second one on constructions of de Sitter by Shamit and Fernando. So yeah, I would suggest perhaps that yeah, if there are things that if you run out of time, if the de Sitter, some of the de Sitter things could move to tomorrow, and so yeah. So please raise your hands.
Maybe there is just in general, yeah, there may be some issue, to focus on some of the aspects of particle physics directly, charge degrees of freedom in string theory. Maybe I see Martin would like to say something to maybe complete with a word or two what I was saying. Martin?
Yeah, indeed. I wanted to comment on the recent work on root bundles that you already mentioned. Yeah, I see you have a nice image of root bundles there. So I wanted to make a comment on that. First of all, for people, it might be interesting to know that root bundles can be thought of as generalization of a spin bundle. So this idea becomes, in a sense, quite natural. Comment number two is on a smooth curve. These root bundles are fairly hard to construct, and the image that Mirjam is showing right now is actually on a very nodal type of curve, where we actually have a means to construct these bundles. That's then called a limit root, and was originally introduced by four mathematicians to illustrate this. The image is maybe good to see, and so the complexity in this sense only becomes that of somewhat combinatorial nature, namely placing some weights in this diagram. So this is quite nice to see that this fairly complex task becomes a quite natural or combinatorial one. And maybe also to towards open questions in that regard. I guess that you should raise two questions. One is these constructions, they are of course in very nodal curves, which are not per se physical. So the one thing that we are currently working on is transitioning from these very nodal geometries to the generic physical ones.
Even like we are looking at the wrong file, I'm afraid.
Yeah, but by the way, we should not be looking at any files, no? I'm being, this should be, we should, I would prefer, yeah, if, right now we should, if we could not see files, if we could just,
No, it's,
It would be better if you turn it off, please.
but I thought I did point out, yeah, maybe you should just.
we saw the
wrap it
picture,
up
we
and-
saw the first nice picture, so that was
Yes.
good, but
Yeah.
but maybe just seeing Martin would be enough.
Yeah, maybe I can fill in for the picture. Okay, so one more open question in that regard that I should mention is these constructions on the nodal curves are in a sense bottom up, so we know very well what we're doing on the curve level. But of course, the full answer from string theory is we're taking the 4D theory or the 3D theory, at least the full F theory construction in this case, and take it down to the curve level. And that, of course, is expected to give some limitations on what root bundles you can actually take. That step, taking it from the threefold potential in M theory down to the curves, telling you exactly which root bundles to take, is one of the conceptual challenges that we are going to explore in the upcoming future. So that's the comments that I wanted to make. Thank you.
Thank you. Any other questions, comments? Yes, Ignatius, would you like to comment?
I have a question, actually.
Okay.
With this, you mentioned in the beginning the history of string phenomenology, starting from various models, starting from the heterotic, going on to deep brains, F theory. So my question is, what have we learned in practice with this, after this, all these years of model building? Of course, we learned tools, different tools to use and construct models. But did we succeed to go closely to the standard model from, let's say, the very beginning times of the heterotic string?
Well, yeah, I thought I gave you a bit of a complementary advances, right, in all those directions. I personally believe that the geometric tools have not only been advanced, but are becoming also very powerful for us to determine large, to be able to construct, engineer really huge landscapes, right? It's not only a question, can you construct a model as an assignment, but really to explore the broader landscape. So the geometric techniques, in my view, have become very important. And in particular in F theory, with toric techniques, we are able to explore many more constructions of that type. Now,
I agree with your assessment, but my question was how close we went to the standard model at the end.
Right. If you look at, the question is, at what level are you asking this question, right? If it's an assignment, can you construct the model that has the exact spectrum of the MSSM, which was somehow the goal in this program? Excuse me.
So I see that Sandip and Wati have raised their hands for a while. Maybe we could get to questions or comments.
But maybe I should just wrap it up, right? Okay, sorry, Gary. So the point is that actually, as far as the exact MSS spectrum goes, right, there are specific issues in each of these constructions. We personally believe that F theory may provide us a bigger landscape with exactly MSSM spectrum because the geometric techniques are more advanced. Now you want to ask other questions like, are all the Yukawa couplings working? You know, what happens in the issues when you include the modular stabilization? Those are all big questions that we don't have better insights right now. But I thought just the spectrum and the exact one, I think we have advanced with geometric techniques and made the progress in that, which I think is per se an important thing because the devil, as you well know, is always in the details. Okay, maybe we should let Sandip, Gary, why don't you go ahead?
Yeah, so Sandip, please.
Okay. No, thanks a lot. I haven't been working actively in this field for some time. So this is more just to also find out from you all about where things are. But even, 10 years, whatever ago, when we worked on flux compactifications, it was already clear that, quite generically, even with supersymmetry, there were vast classes of compactifications which were very different from Calabi-Yao's. They were, they could be complex manifolds with torsion, that was known, but they could also be manifolds which were not even complex. They did not have an integrable complex structure and so on. And that seemed, in a sense, very exciting because it opened up these huge new classes of manifolds to study. And I just wanted to know where things are in terms of understanding those manifolds, their moduli spaces. Are there the analog of, Yao and Calabi's results and so on, where the field stands? Thank you.
Right. So I think there are efforts not only in extending the space of compactifications, but also go more into a more microscopic constructions. So I think the question that sometimes people would ask is, having a sketch, like all these branes, fluxes, wrapping around cycles, having a sketch does not mean that we are guaranteed to be able to put them together to give the proposed four-dimensional effective field theory. So I think, as Pablo alerted to in his short presentation, there have been a lot of efforts trying to lift all this four-dimensional effective field theory ingredients into a more microscopic 10-dimensional description. And so when we have this, when we up our game, we may be able to quantify more precisely the type of corrections that Dine-Seifer problem typically suggest that they are there. So one would have to be looking more microscopically into these constructions, or maybe Pablo or Miguel could comment further on that.
Well, I think it's an interesting question, but also I think it's related to something Kundrum said before. How complicated are the models that we want to tackle first? If we want to achieve something something like a positive CC, if we fail in Calabi-Yau, then next take a more complicated setup and step by step, because otherwise we end up with many models and none of them fully understood. That's, I don't know, I have a finite amount of time that I can spend on each of them.
Okay.
Right.
So
Okay.
maybe in the order, it may not be exactly right, focusing in one direction, but maybe Wadi should have a chance to ask questions, comment.
Sure. Thanks, Mirjam. Actually, I just wanted to add a little bit to what you said, Mirjam, in response to Ignatios's question about, where have we gotten with this? And you commented, Mirjam, I think very accurately, that F theory gives us, this very large range of things. I just wanted to add a few comments to that I think some of the reasons that in particular, this F theory approach and combining that with some of what we've learned about string universality and Swampland things has really given us some new insights, is first of all that F theory really gives us a global connected view of a very large class of vacua. And this is most apparent, for instance, in 6 dimensions, where all the different elliptic Calabi-Yaus that F theory uses are connected essentially into a single moduli space, connected by various extremal transitions. And that huge moduli space with hundreds of thousands of branches matches very closely in the sort of string universality Swampland story with what we see from 6 dimensions. So from F theory, we see, first of all, a non-perturbative, but also a global picture that, at least in 6 dimensions, seems to give us a very large part of what we know is possible in quantum gravity. And so extending that to 4 dimensions, where we really have a connected set of geometries, even though there's a superpotential sitting on that, there's still a connected set of elliptic Calabi-Yau fourfold geometries, again, all connected by extremal transitions, so forming a kind of a global moduli space. And I think that gives us also the ability to ask questions like, what is the naturalness of different constructions of the standard model? I mean, Mirjam mentioned there are these quadrillions of constructions through certain kinds of tunings. There are other ways you could realize the standard model. And I think we can begin to ask quantitative questions about which of these constructions require more fine tuning and which are most natural in this very large connected landscape. So I just wanted to add those points.
Yeah. Well, thank you, Wadi,
Thank
for
you.
recording so nicely. Yeah, what I try to point toward. Thank you. So, Gary?
Next is Thomas. Right. I think you are the next. Thomas Vermeet.
I'm here. Can you hear me?
Yes, I can hear you.
Yeah, thanks. I have more a question to the audience. Since we started talking about, the history, where are we going? What did we achieve? The thing that I always find a bit surprising is that many of us do all this highly technical work on finding, spectra, kind of gauge groups. But the weird thing for me is that shouldn't step one be, in the end, always moduli stabilization, finding the vacuum? And in particular, a very crude and simple criterion is, can I even use an effective field theory? And to be able to use an effective field theory, one of the requirements is what we call scale separation. Okay, so the very simple fact that I can stabilize extra dimensions, I can hide them from my view, is such a basic thing if you look at our own world. And the fact that there was even a conjecture by some of the people here suggesting this could even be impossible, say for ADS vacua, to me shows that one of the most fundamental things about string pheno, one of the most foundational things we don't even agree on. So isn't it a bit strange that as a subfield of string theory, there's so little focus on this? I think it would be great if at some point the majority could say, we achieved a consensus. We say there's no doubt we can reach, scale separation or not. Because I think one of the things I wanted to add, and then I'm done, is that this whole question of, say, something simple as moduli stabilization and scale separation and the use of effective field theory also relates to a fundamental choice we have to make. Do we believe that, compactifications are the way to go? Or is it maybe, brain worlds? Maybe brain worlds are, they seem to be really two different things. And I think it's important to decide between the two. What would be the way forward? And I feel these are such simple questions, and they're sort of in contrast with some of the highly technical aspects, say, done by the F-theory community. I find it a bit surprising. So I'm just interested in somebody's opinion on this. Thank you.
Okay.
Andy Taker.
Let me just say a non-physics thing. If people can keep their cameras on, I think it makes it feel more cozy. So if you can, of course, if your internet allows, keep your cameras on so that we feel like we're all in the same room.
Can I just make one comment about what was just said about ADS non-SUSY and just add to it if I can, or I can wait?
Please.
Just 2 minutes, which is, I mean, isn't this a great question to try and address with the Bootstrap program, which is, can you get a non-supersymmetric ADS with a large gap? It seems like the simplest non-SUSY kind of question of some relevance to phenomenology we could go after, using the Bootstrap. I just wanted to ask you all what you felt. Is it something that could hopefully be tackled using those techniques? Sorry.
I think Thomas would be the one responding to your question.
I just want to add to what Sandeep said that, well, there's a chunk of people trying to do this. It seems to be very complicated. But let me add that the question that you're asking is not particular to non-SUSY ADS, right? So this question of scale separation, or just using effective field theory that it's allowed, so scale separation, you can ask that question for supersymmetric KKLT, for instance. And we should try to find the CFT dual to KKLT, at least the supersymmetric ADS one. And the same for these DJKT solutions. And people are actively trying at the moment. And I think the main hurdle is this observation by Polchinski and friends that, you can sort of, bootstrap bounds can become trivial in a way that you always kind of get they always can get consistent with some kind of a naive effective field theory that I'm writing down. It doesn't mean that it will not work, but this, I think, is the main obstacle that people are having in this subfield.
Thank you.
Okay, so
I think Eva is next. Just one thing, Miguel was waving, so I think it probably means that he has a comment related to precisely what is being discussed.
Okay.
That's right. I just wanted to make a quick comment. I really like Sandeep's idea. And one context in which we maybe can make a lot more progress and sidestep a little bit the objections that Thomas pointed out is in the context of ADS3, right? If you have an ADS3 scale separated vacuum, and I think Thomas and friends constructed examples of this by mimicking the DGKT logic, also on type 2A on a G2 manifold. So that's something you can actually try to study from the dual CFT point of view using all the techniques that we have that are exclusive to CFT2s like modular invariance and stuff like that. So that's probably a promising element.
Thank you. Thank you very much. Okay,
so I think Eva is next.
Okay, sorry, I'm not using my video because I'm having internet troubles today, which I'll solve by tomorrow, I hope. So there's a lot to respond to here. So one of the young people, I apologize, I forget everybody's name, raised the question of what the status of KKLT is. And as someone who's followed that subject a lot over the years, let me add that I think with this last question that was raised about, are there singularities inside of the manifold? I think there was a rebuttal to that by Jaka Moritz. And also, I think the assumptions behind that were strong. That is, they assumed that sort of all the charge was coalesced in some region of the manifold, whereas it could be distributed much.
I'm trying to wave my hand, but I can't.
Yeah, we stopped hearing Eva for a little bit.
Right. So thanks, Eva, for the comment. I agree with your comment. Can you hear me? I am hearing some echo. It's okay.
I think there was some connection problem.
Trying to complete her.
Sorry, Eva, if you can hear us, your connection, I think, is not cooperating. I think it's not possible to understand.
So,
Oh no.
Oh, now we lost.
I think we lost
so
her.
maybe in the interest of time, Pablo could say a few words, and while we're waiting.
I was just gonna say that I agree partially with what she said. There's some work, and I think the authors are not here, unfortunately, of how to possibly relate this KKLT singularity. But I don't know what is if that's the way to resolve the singularity, or what would be the final status of our understanding, whether that would change our understanding of the effective field theory of KKLT or not. But I do agree with another comment you made, is that these seem to be genericity questions that would say, like, if we treat the D3 charge homogeneously, then it's difficult to reproduce the standard picture of KKLT, but it's not impossible. So maybe this will just cut out chunks of the landscape, not. And that was my question, whether we believe these problems are generic problems, or that will be resolved simply by narrowing the landscape of possible compactifications, or truly singular problems that will change our understanding of KKLT. And I agree with Eva that it seems to me that there's some notion of genericity in these problems. I think this will be discussed in more detail tomorrow. It's probably more appropriate. I brought it up because the discussion is going to be at my 3 a.m. time here in Korea, so I'm gonna miss it, unfortunately. Sorry about that. But that's.
I think there are two parts. I think there are two parts of that issues. One is whether the singularity is resolved, and the second part is whether we have control of the low energy effective field theory. And it's true that the singularity that was pointed out in the reference that you cited was there was a proposal to resolve the singularity, but I think it remains to be shown that the low energy effective field theory of KKLT matches with this strongly corrected bulk. I think this is an open problem.
I believe Sandeep was waving, so maybe he has a comment related to precisely.
Please.
I just wanted to say, I didn't want to get into KKLT because I thought we have a whole session, and maybe we'll do that. Since you brought it up, I mean, this singularity issue, as far as I know, is in some particular way to arrange the charge and so on. At least I'm not convinced that it's a generic feature of the general KKLT mechanism. Now, if you like, we can talk about it later. If you say generically, the way you do the KKLT construction always gives rise to stringy curvature regions, and there's a proof of that. Okay, I at least don't know of that. Okay, so, but we can perhaps postpone it for tomorrow. And
it also depends on what you mean by KKLT. Do you call the bulk that is strongly corrected KKLT? If so, then that's a different. It's a different problem. So. But as you said, there would be a more detailed discussion about specifically about the zeta constructions tomorrow. We could continue that on as well. And I think there was a hand raised by Ander.
Irina?
Or Irina? Irina, I think Irina is first.
Yes. Irina, maybe you could comment.
I don't mind who was first. Okay, yeah, I mean, I had a general comment about what we are discussing, because it seems that people are worry about where are we, how much we have learned, how useful is all these approaches. And I personally believe that we are at an inflection point, in the sense that we have learned a lot about string compactifications, how to construct some things. But I think it's the moment to gather all this information and of course continue, but also gather this information and try to extract what are these lessons and in which lessons quantum gravity really matters. So I don't think it's just a matter of whether we get the standard model, but try to identify those points in which quantum gravity have something additionally to say beyond quantum field theory and so on. And try to connect these general lessons with other approaches like ADS-CFT, positivity constraints, and all the tools that we are learning from other fields. So I think sometimes we get, I don't know, lost in the technicalities, but yeah, I don't know, I would like to bring back like some of the questions that Miguel, Pablo, and Lynn suggested, that where quantum gravity matters. Does it matter to engineer hierarchies, naturalness uses? Does it matter to understand scale separated vacua? Is something more difficult, it's something easier in string theory? Or the sitter, I mean, of course, it's also a clear topic, but where are let's try to identify like some simpler universal things that we don't know yet how to engineer, and that quantum gravity can be behind that. No? And I think this is the inflection point that we are observing, and that it's obvious also from all the talks in the string phenomenology conference. I mean, that there is a change of paradigm in that respect, and that we try to open and connect with other fields. So, yeah.
So thank you, Irina.
Wadi, I'm sorry, but Wadi seemed to have your hands up. Yeah, still for some further comment, or?
Oh, no, sorry, that's just an artifact. I forgot to take it down.
Apologies. Then Kumrun, I saw rose a hand. Yeah, please go ahead, Kumrun.
Yes, just a comment. I think that Thomas actually reflected the view I have also, that first of all, finding stable vacua in string theory is extremely important. And to me, this is the single most important thing we should be doing in string theory. The amount of effort, I think, by the research going on in string theory is not commensurate with the importance of this question. I think a lot of effort is going on to questions of black hole holography, which is all fine, but we want to connect ultimately to our universe, and this is not getting us that close to that question. I think the community should redirect itself, at least to a great extent, to get tools to answer these difficult questions. Clearly, we have a lot to go. Clearly, it's difficult, but clearly we have begun to answer some of these questions. And I think that without more of the community getting engaged, that will be unfortunately going to be delayed. So I want to make this appeal to our string community to put more efforts in the directions of trying to connect to string theory toward the real world, which is not happening, unfortunately, in most research.
Okay. Agreed.
I think Eva is back. Would you like
hi,
to...
can you hear me?
Yes.
Can you hear? Okay, thank you. I just wanted to say a couple of more things regarding this kind of meme about scale separation. It really is related to a very simple plot that Gary had, the one where he referred to the Dine-Seiberg problem and how you need the three-term structure to get de Sitter space, which has been known as that was the first thing we noticed in studying the cosmological constant 20 years ago. And it's that three-term structure with a large number that allows the three terms to compete that enables a tuning of the four-dimensional Hubble to be weaker than the internal curvature. So that it's just that. It's really a dumb, simple, mechanical thing. And so that's how it works in all the models, and that's why we get scale separation. One thing to say about the difference between de Sitter and anti-de Sitter is that there are some really interesting ironies in the subject. So for some purposes, de Sitter is simpler. Here's an example. In anti-de Sitter, if you have a kind of landscape, okay, if you have decays that are available, well, they hit you in an ADS time. And that's because of the asymptotic volume contained in ADS. However, in de Sitter, a metal stable potential energy gives you a solution that indeed lasts an exponentially long time. So in that sense, the de Sitter metastable solutions in the landscape are exponentially more stable than the corresponding ones in anti-de Sitter. But in any case, the separation of scales, in my view, is really a non-issue. It has to do with the three terms. If you want to know what the large number is in the various constructions, it's large D in the original constructions. In the power law context, it's W naught in the KKLT constructions. It's large genus or other parameters in hyperbolic spaces and hyperbolic compactifications. It's various topological quantum numbers in the large volume scenario. That parameter is known, and that's why we get scale separation. It's not too hard to understand. The last thing I want to say is the cosmology session, we're planning to kind of keep it more down to earth. It'll be more about the sort of clear UV sensitivities that Gary skipped over. So if people do want to make sort of grand statements about attempts at no-goes and so on, I think this session would be the one to do it in. One thing I would ask though is that if you make such a conjecture, it be consistent with all of the ingredients we know and all the models that we have. So in that spirit, for anything to do with cosmology, inflation, or de Sitter, it's important to incorporate the leading terms in potential energy, and that includes the D minus D critical term and the curvature term, which is typically positive potential energy, along with all the other sources that people talk about. So for any kind of no-go theorem, those must be addressed.
So we have the discussion leaders for the de Sitter construction tomorrow here. I think Fernando is here. If this is going to be discussed, maybe we could move on to the next questions. Otherwise, we could keep going for a little bit. I don't know how much time we have.
Yeah, as I said, so if we are going well, there's no, we can go for a few more minutes.
So for instance, I suppose Shamit and Fernando will go through some of the issues that we are discussing today in more detail. And maybe we could go to the next who asked questions. Is that Ander?
Ander, yeah.
Sure. So I have a question following a bit what Thomas started and Kunrum followed. Well, I've been on board in the field for, I don't know, 10 years or so. I have the feeling that, say, 20, 15 years ago, that there was more activity of people working, well, trying to contact the string theory with observations. And I have the impression that some people, well, maybe took another direction, maybe because they found something more exciting, or, well, I'm actually wondering, I would like to ask the more experienced people that maybe they were working in this field, why they decided to take this direction. Because I had the impression maybe that it was that, I don't know, well, there was no significant progress, or they felt there was no significant progress, or, well, whatever the reason was. Yeah, I wanted to ask more experienced people what the reason was.
Oh, yeah. Look for someone experienced, was doing phenomenology and is now doing something else.
I mean,
there are plenty here, so I'm not one of them.
Well, if anybody is willing to answer or say something.
Well, I don't know. I'm certainly guilty of that. I'm really guilty of that. But I don't know. I mean, you don't listen to the older people, actually, is what I would say. They're obviously wasting their time. But I don't know. I mean, others should say, others are more distinguished. But I don't know, the field, in a sense, new questions come up and I mean, these are very important questions, but you need an angle to attack them. And for example, for de Sitter, it just seemed worthwhile to try and address some of the conceptual questions, which are also tough. I don't know. I mean, I don't know. Don't listen to the older people. They're wasting their time.
Good advice.
Yeah. Sakura is young and she wrote in the chat. Sakura, don't you want to chime in?
Say something. I mean, I can say something. I actually don't really want to say a lot because it might have a lot of background noise, but I think there's perhaps another question that you're really asking, which is to what extent do actual phenomenologists care about this? And I think if you're doing string phenomenology, you need to ask yourself this question, right? Am I actually doing something where a happy-age person would actually go out and seek out those results? And I think for some of these things, this was certainly for a very long time the case, but then with sort of the death or the almost death of supersymmetry, maybe that has stopped a little. And so I think that's certainly a factor, and perhaps other people want to comment.
Yes. It's a revival with the Swampland program on that, no?
Yes.
It's even more fino.
Absolutely.
Yeah.
I think he was asking a question about people building models like, you know, we used to do in F-theory.
So I think the phenomenologists are paying much more attention to string theory these days, precisely because these questions that are arising in Swampland are very close to things that they are interested in. So that actually brings an opportunity for us to connect with phenomenology as well as bring their insights into it. So I certainly think that that's a good golden opportunity for our research, but the questions are still tough. You know, getting the exact model and so on is a secondary question right now, in my opinion, because even the basic questions we're still not debating, whether we can get the minimum and so forth. So there are these kind of questions we really need to focus on and try to come to some kind of better understanding.
Maybe Dimitris and then Nathan.
Mm-hmm. Hi. So I have a sort of elementary question of principle, really. So suppose we have a large enough sample of string vacua, whatever that means. I'm wondering, what do we do with them? I mean, should we think about summing over all of these saddle points to get the full quantum gravity path integral? And how far can we go in that direction? Suppose we did have all the saddle points that are relevant, or whatever that means. I mean, would we actually think about summing over them? And if so, to what extent is a specific vacuum that important?
Well, why would you want to sum over it? If you find all of them, then I would check which one of them looks like our universe and we're done. So I think it's
well, the thing is that if you have a path integral over some theory, there was this talk actually by Neil Turok that got me thinking, that he was saying that you can rewrite the full path integral as a sum over its saddle points with certain phases. And that was quite a generic statement.
Oh, you're talking about the finite action processes. If you choose a background, to go to any other one, typically when you fix the background, might be different. So
you fix a boundary conditions?
Yeah, you fix the boundary conditions.
And then I'm wondering whether we should really be integrating or summing over
there's
all
no
saddle points.
Of course, those questions that you're asking will become important for early cosmology, and whether or not there's, to what extent our space is compact, to what extent we can shuffle from one to the other and all that. But I think for present stages of the universe, you just pick the one you're ending up with if we had all the answers like that. Because if you have a non-compact space, there's no sum, right? There's a super selection.
I don't really understand where your reasoning comes from.
Super selection, like, well, how do you freeze the web of a field in dimensions bigger than 2? You cannot integrate over the web of the fields. You freeze them. Why? Because of the infinite action that you need to change them at infinity.
Sorry, I'm a co-host, so I can't raise my hand. But just on that question, I mean, I think it's an a point that hasn't really been made that connects with that question is that, I think it's probably ultimately very important that we understand how to actually get some microscopic kind of framework where some cosmological solution can be embedded. And if we had that, then this could help answer these questions of what is playing the role of some kind of gravitational path integral or whatever. We have that for asymptotically ADS. We don't really have cosmology, but I think if we do, then
yes,
that will help answer all of these questions.
Yes, cosmology is a golden opportunity, I think, for string theory.
Maybe Nathan still, yeah.
Nathan.
Know how to wave my hand. I think the question was answered about why people left phenomenology, but I mean, I think it's something that older people maybe know, that when there's a new experiment that's going to be built, I mean, there's a great motivation to do phenomenology. So, I mean, I think I remember when the super collider was supposed to be built, there were lots of people moving to phenomenology, and the LHC, I think, inspired lots of people. And as Kumar said, when there are new cosmology experiments, I think lots of people from string theory will go try to find predictions for that too. So that was all. I mean, it's kind of obvious. But.
Right. I think we would take string phenomenology to include not only particle experiments, but also cosmological experiments. There are many exciting possibilities that we will hear more about tomorrow.
Okay. Sorry, I see Eva have hands up, but maybe we should let Louise make a point. Louise Ibanez. Louise?
Yes, I'm going there.
Yes, we hear you.
I just wanted to make the comment that I think the phenomenologists care about string and string phenomenology. They have borrowed, particularly beyond the standard model phenomenology, a lot of ideas from string theory. They are eager to learn new ideas coming from our field. Remember extra dimension, remember now the constraints on action couplings or in action inflation, etc., in cosmology. And I think that's new ways to understand the hierarchy problem. They are really following. I mean, the phenomenologists who are more on the theoretical side, but there is a large fraction of those. And I think with these new Swampland ideas, they are also very attentive because perhaps we can learn new ways to understand the hierarchy problem. I also believe that the story of the neutrino masses and the cosmological constant would be a very important hint. I find it interesting that there could be such a connection. And I think that we should focus, if ideas like the Swampland ideas come with a very definite prediction, like for example, the neutrino, lighter neutrino mass is such and such, and that would be very important for the whole program. Or, for example, understanding strong CP problem from these ideas or other naturality problems, or a good simple explanation of the hierarchy problem. Why really quadratic divergences really do not matter when analyzing the mass of the Higgs, for example. If the fact that the scale of supersymmetry breaking, for example, the fact that the standard model without supersymmetry has becomes unstable at 10 to the 10 GeV or so, what's going on there? String theory can tell us something about that, the stability of the standard model. I think the string theory has the potential to give, is a natural source for new ideas to understand, to make contact between quantum gravity and the real world. So I'm still optimistic.
We like your optimism.
I would suggest either we conclude with an optimistic note. Eva, is your comment related to the sitter or something? If it's the sitter, maybe we'll postpone for tomorrow and end on an optimistic note, I would say. If not... it
was on the subject of supersymmetry and should that cause people to leave the field? Was that Sakur's question, basically? Sorry, I do have the internet problems. Anyway, I think that that's a very, very interesting point because there's kind of two narratives in the field. One is kind of bottom-up supersymmetry, grand unification, et cetera. And the other is, well, what do we generically have in string theory? And almost everything is not supersymmetric at low energies. I mean, but those are really 0% of the string backgrounds. And make no mistake, the ones that are not as supersymmetric are perfectly controllable by standard methods of physics, the things we do in empirical physics all the time, including but not limited to perturbation theory, numerical method, mathematical theorems, et cetera, et cetera. So I find this question about supersymmetry extremely interesting for this reason, because there's a tension between these two points of view. But from the point of top-down string theory, there's nothing that forces us to supersymmetry. And if we look, in my view, if we look just honestly at the space of string backgrounds, it works quite in the opposite way. So it's we have generically positive potential energy, good for cosmology, and generically we don't have low energy supersymmetry. So it's perfectly consistent with phenomenology. And yes, regarding the connections to cosmology, which already exist, we'll cover those tomorrow.
Thank you.
So maybe on this note, we should wrap up this discussion, which actually went quite over time. So
yeah,
that's
great
a good
fun.
sign too, right? And
thank you very much, Mirjam and Gary and everyone.
Thank you.
Thank you.
Bye.